Now, try to find the inverse of the last two on your own. So try to find the inverse of a squared, like you're trying to find a formula for that, and the inverse of ka. What I'd like you to do maybe here is use a solution that uses linear transformations. And here for ka, something that uses algebra. So pause the video and try to do those two, and I'll show you the solution. So for a squared, um, so assume again it's the standard matrix of an inner transformation. Okay. And here a squared, so you can think of that as a times a. Okay. So it's a composition of two linear transformation, one which is the linear transformation with standard matrix A, and it's actually the same one again that's applied. So you apply T of A again, and you get A squared X. Okay. So how do you go backwards? Well, what's the inverse transformation of the linear transformation with standard matrix A? It's the linear transformation with standard matrix A inverse. And if you go backwards here again, you get T of A inverse. So if you compose these two together to go backwards, well, what's going to be the standard matrix? Well, if you start with vector x, you apply A inverse, you get A inverse x here. You apply A inverse again, you get A inverse times A inverse x. So that's the standard matrix. It's A inverse times A inverse. So there's a nice way to write this down. So of course we could say that the inverse of A squared is A inverse times A inverse, but I hope you'll like this notation. We can write it as A to the minus 2. So what's kind of nice is that the rule of exponents that apply to numbers, it also apply to matrices. So A to the 2 to the minus 1, you can multiply the exponents together to get this one. So we could actually write in general that the inverse of A to the power n, if n is an integer, so the inverse of that is A to the minus 1 raised to the power n, and we can conveniently write this as in the following way. We can write it as A to the minus n. So this is really a notation here that we use. Okay. It doesn't, by the way, this is not 1 over A squared. That makes no sense at all. That's a scalar. That's a matrix. You cannot write the division between a scalar and a matrix. So this you cannot write, but you can write this. This is completely okay. A to the minus 2, A to the minus n. It's equal to A squared to the minus 1. The other one is an to the minus 1. Oh, by the way, this is also the same as if you write A to the minus 1 to the n. Well, what is that? That's A to the minus 1 times A to the minus 1 n times. Well, using the property AB to the minus 1 is B to the minus 1 A to minus 1, which can be generalized in the following way. If you have ABC to the minus 1, that's C to the minus 1, B to the minus 1, A to the minus 1. If you replace C and B by A, you'll get A to the minus 1, A to the minus 1, A to the minus 1 is A times A times A to the minus 1. So if you have 3 A to the minus 1s, well, you can regroup the A's together, multiply them, and raise that to the minus 1. So what I can do here with, if I have it n times, it's basically A times A times A to the minus 1, and I have A's multiplied together n times. So that's a to the n, because I've got a multiplied with itself n times, to the minus 1. So what that shows is that here these two are equal, and you can essentially permute the minus 1 with the n, and all of that is also equal to this. So the big thing here is that if I write this or that or that, they all mean the same thing. Okay, so this notation that we've introduced, which was used initially for this, you could wonder whether that is also equal to this, but this is what I've just shown you. So whether you put the brackets, whether you have a to the minus 1 to the n or a to the n to the minus 1, it's all the same. It's all the same. Okay, and you have this also with numbers. If you have 2 to the minus 1 to the power 3, that's the same as 2 to the 3 to the negative 1, and in general we write 2 to the minus 3. So these properties of exponents that apply to real numbers, they also apply to matrices. So that's kind of nice to know.